good morning, good afternoon, and good evening. Okay, this is Kevin here. So I'm from Sungrow. Today I'm very happy that OPAL-RT can provide this such opportunity to let me share some experience that we are using hardware in the loop simulation and real-time simulation for our power converter and energy storage system applications. And I just saw the poll, the results of the poll. A lot of you are interested in converter control HIL simulation. So I'm happy that I'm gonna share some ideas and experience from our daily work. Without further ado, First, I'm gonna introduce our understanding of hardware in the loop simulation. Then I will show you what Sungrow use real-time simulation and HIL simulation, show you the HIL simulation lab we had here. And then we're gonna share some simulation cases. So first, please let me introduce a little bit about Sungrow. For this, you might haven't heard about Sungrow. Sungrow was established in 1997, and the headquarters is located in Hefei, China. And at the beginning, we are a PV inverter manufacturer. Now, our two significant business, including PV inverters and energy storage. So now we have, globally, we have three manufacturing bases, one in headquarters Hefei, China, and one in Thailand, and another in India. And we have 6 R&D centers in Shanghai, in Hefei, Shanghai, Nanjing, Shenzhen, and Munich, and Amsterdam. We have 20 plus international subsidiaries, just showing here from North America and Europe, and also Australia and Northeast Asia. And our network covers like 170 plus countries. So this is from the revenue chart, you can see the market is expanding very quick. Last year, our revenue reaches 10 billion US dollars. And the total installation of PV inverters for last year comes to 130 gigawatts, which is 100 times than the year 2012. Here's our PV inverter products. We do have modular inverters and string inverters, also have a residential inverter. And it's being ranked the #1 in global PV inverter shipment. And here's our energy storage system. So we cover utility scale energy storage and business scale storage system, and also residential storage. So last year, our shipment of storage system reaches 10.5 gigawatt hour. And besides PV inverters and energy storage system, we also have business in renewable energy plants development, wind power converter, and inverter and charger for electrical vehicles. And also we have hydrogen equipment manufacturing as well. So actually across all the business, the HIL simulation is used all across all the business departments. And you may wonder why it is so popular that HIL simulation is in Sungrow. So in the rest of the presentation, I will share with you why this is so popular. So then let me explain from our perspective what hardware in the loop simulation is. So a lot of colleagues that haven't heard of real-time simulation or hardware in the loop simulation, they come to me and ask what it is. So I will always use a metaphor to help them to better understanding what it is. So let's consider a racing game and a power system simulation. So in the this graph shows a real-world racing. So not every of us has a chance to go on a track or to afford a Ferrari or Lamborghini in our real life. So, but we still want to enjoy excitement of racing cars. So what are we gonna do? We can play video games, right? Like Need for Speed. So, but for the video game, you just use the console controller and watch the screen. You cannot feel the motion and acceleration, right? Then here comes a VR. So that's kind of bridge that connects video game to the real world racing. So it's give you a more immersive way to enjoy the racing. Like you can feel the actual acceleration and braking. So compared to our real power system simulation, so real world racing equals to real power system, right? And video games just like digital simulation, like Simulink or Piscat. And hardware in the loop simulation is the VR of power system simulation. So the basic I think the base for hardware in the loop simulation is the real-time simulation. You have to achieve real-time to enable hardware in the loop simulation. So what is a real-time simulation? From this clock here, we can see it's running fast than real-world clock. And the second one is slower than the real-world. Only the third one is synchronized with the real-world clock. So we call the third one real-time simulation. Okay, once we can achieve real-time simulation, actually we have a new pathway of simulations that we can connect. I consider real-time simulation as a pathway that connects digital world and to our real world. We can build PV modules, batteries, converter, IGBTs, or grid and loads in real-time simulator, and then connect our hardware controllers to the system, like inverter or PCS controller, BMS, EMS, and PPC controller, and etc. So as Thomas mentioned that there's a power hardware in the loop simulation. The one I'm talking about here today is controller hardware in the loop simulation. So in Sungrow, we mostly use controller hardware in the loop simulation, and the rest of this presentation is all about controller hardware in the simulation, in the loop simulation as well. So I even asked ChatGPT what's the benefits of HIL. So ChatGPT gave me 8 bullet points. I'm not gonna go to detail of each one, but I pick up 3 most significant benefits of HIL provide us from our daily work perspective. The first is enhanced testing and validation. So the realistic testing environment HIL provides can help us to detect software issues in an early time. So that is help our R&D teams to accelerate their software development for a significant amount of time. And the next one is safe testing of edge cases. So we can test extreme hazardous scenarios. For example, for all kind of grid contingencies, like voltage fluctuation, frequency fluctuation, and phase jump. So normally this cannot perform in a real power plant. Otherwise, you may jeopardize the safety of the network and get a penalty from the grid. The last but not least is time and cost efficiency. So it accelerates development cycles by a large margin. So it reduces need for physical prototypes. And when the physical prototype is ready, so 90% of the software test has already been done on HIL. Another reason besides R&D needs, R&D requirement of the HIL is actually the marketing and the solution team also requires HIL simulation. That is because in a lot of areas and countries, they require every grid integration projects to provide HIL simulations. One example is Australian AEMO, and I think that's the first grid operator that requests HIL simulation for their grid connection application, probably around the year 2016. And then now the US ERCOT and California ISO is also require the benchmarking of the pure digital power simulation to benchmark with HIL tests. And also the HIL test already being included in IEEE standards as well. So, and recently, as I learned that in Middle East, especially Saudi Arabia, from the year of 2023, all new grid connection projects has to provide HIL simulation results and all the network connection studies with HIL. Okay, now I'm gonna have introduce a brief introduction of our HIL simulation lab in Sungrow. So actually, we have more than 20 OPAL-RT simulators. Most of them are OP 5000 and 5700. Due to the FPG capability, so we can simulate very fast switching converter devices up to 60K to 100K. What we use hardware in HIL for testing, we mainly use that for two types of tests. The first is individual converter controller test. So we have PV converters or energy storage converters or wind power converters, and also EV drive units. So we build these models like PV and battery and wind turbine in our real-time simulator, and we connect their converter controller to the OPAL-RT system via I/O and DI and I/O and the communications. So then we can run the whole system in a closed loop. That's the first type of simulation we do normally. And the second is power plant controller HIL simulation. So in this case, we can build like microgrid or large-scale power plants in the OPAL-RT simulation system. And then we connect BMS, EMS, or PVC real controller to the system to test their control algorithms. And another powerful tool is thanks to the comprehensive pathing API that OPAL-RT provides, RT Lab provides actually. So we can use pathing, pure pathing scripts or professional automatic test case managed systems to build automatic HIL automatic test bench test platform. So we can do automatic data collection, analyze, and plot the figure. And also we can automatically generate the test reports. So without human on site. So it's very convenient. It's like we just press the start button, and then at the end of the day, then we come back to the next day. All the tests has been done, like hundreds of tests has already been done, and also the report is generated. And another part of this is it can generate tons of data that we can use for our AI model training. So it's another advantage that if you put together the automation and RT Lab, it will generate, it will largely increase the efficiency of testing. So here I'm gonna share some simulation cases that we've done previously. The first one is the simplest, just one inverter controller connect to one real-time simulator to run all kind of grid connection tests. So we built a big grid HIL test platform, so we can test both grid forming and grid following control strategies. We can test their extreme low SCR condition, like we push them to the limit to see what's the lowest SCR the inverter can work. And also we can perform consecutive high voltage read through and low voltage read through tests, and also frequency response tests. And we developed an inverter impedance sky test too to generate the border plot of our inverters. Here's another usage that we use HIL for model validation, because HIL just takes the actual control hardware from our actual product. So it represents the controller's actual performance in the real product. So we normally use this as a benchmarking for other digital simulation models. Here's a comparison of another digital model with our HIL simulation. Okay, another case is power plant controller HIL test. So in this case, so based on the last only inverter test case, we here included another PCS or EMS. So it connect via IEC 104 or Goose communication protocols directly to our inverter controller. And then we measure the voltage and current at the POC and send to a smart meter, and the smart meter will connect to PPC controller. Then the PPC generates control algorithms based on the voltage and the current measured at the POC and send a dispatch signal to our inverter controller. So in this case, we can mimic a whole power plant. Instead of building a real power plant to test the PVC, we can run almost all the tests of the PVC's function via this HIL test platform. Here's another case that we use two simulators run in synchronization. So in this graph on the right-hand side is our best system hardware in the loop test system. So this is mainly to test our BMS. We have our BMS controllers connect to our cell models in the real-time simulator. And the other side is the PCS controller HIL test platform. So we can use fiber optics to connect these two devices, these two real-time simulator, and run the whole system simultaneously. So in this case, we can simulate like thousands of battery cells. We together with our BMU, our local controller, and the power plant controller, together with our PCS. Here is the actual project we run in our HIL system. So that's a project that's a that's a power plant black start project. It's one project in the US. So before we went to the set, we run the whole process on our HIL simulation, and we identified some of the control algorithms issues before went to the site and fixed at home. And when the team goes to the site, when the team goes on site, so it only takes days to have the system running smoothly. So that's the whole process we've been run on our HIL simulation platform. So upper side is the current, and the lower side is the voltage. So the first part is multiple PCS startup in synchronization. You can see the voltage is built up gradually, and then we come to the main transformer excitation, and you can see the surged current that's due to the saturation of the transformer, and then some resistive load cutting. Then the other current surge is motor cutting, and here the steam turbine just starts up, and our PCS, the voltage here, the PCS just changed from grid forming mode to grid following mode. Okay, that's pretty much all for my presentation today, and thank you for everyone's attention. Thanks.